All right, today we're going to crack open the secret language of complex numbers. We're going to find a much more elegant and intuitive way to handle them, turning what feels like clunky algebra into some really simple visual geometry.
You know the feeling, right? If you've ever had to multiply complex numbers, you know the whole routine. You got to use the FOIL method, combine all the like terms, remember that I squared is -1. I mean, it works, but it's a total slog. And don't even get me started on division. You have to find the conjugate. It's just not clean.
But what if I told you there's a much cleaner, much better way to do all this? And it's not just about memorizing some new formula. No, it's about a fundamental shift in how we think about what a complex number really is. We're going to stop seeing it as just a point on a grid and start seeing it as a vector, with a direction and a length.
And that switch in thinking brings us to the core idea for today, moving from the grid to geometry by using what's called the trigonometric form. And trust me, this is where the magic really starts to happen.
So take a look at this. This shows the new perspective perfectly. Instead of just thinking about an x-coordinate and a y-coordinate, we're describing that exact same point in a totally different way. We're talking about its direct distance from the center, we'll call that its length, or r, and its direction, which is just the angle it makes with the positive x-axis. We call that angle theta.
So let's break those two parts down. First up, we have the modulus, r. All this is the length of the number, the straight line distance from the origin right out to our point. And we find it using a tool you already know, the Pythagorean theorem. It's just the square root of x squared plus y squared. Simple as that.
And the second piece of the puzzle is the argument, theta. So if the modulus is the length, then the argument is the direction. It's the angle that tells us exactly which way our number is pointing. And we can find it pretty easily just by looking at the relationship between the x and y parts of our number.
Okay, so how do you actually convert one of these? Well, it's basically a two-step process. First, you calculate the length r. Second, you calculate the angle theta. And then you just plug them into this standard form right here. That's literally all there is to it.
All right, so we've put in the work to change our perspective. Now, let's see the incredible payoff. This is where operations that used to be a real pain suddenly become almost effortless.
So let's start with multiplication. When we multiply two complex numbers, something really amazing happens with their geometry. We get a new number, and you can see its angle is simply the two original angles added together.
I mean, the rule could not be simpler. To multiply two complex numbers, you just multiply their lengths and you add their angles. That's it. No more FOIL, no more messy algebra. It's that clean.
And here's what that super simple rule looks like as a formal equation. You can see it right there. The lengths, r1 and r2, are multiplied together out front. And inside, with the cosine and sine, the angles theta1 and theta2 are just added up. It's exactly what we said, just in math speak. And now for division. And you can probably guess, it follows the same beautiful logic. When we divide one number by another, the new angle we get is just the difference between the two original angles.
And here it is in plain English. To divide two complex numbers, you divide their lengths and you subtract their angles. It's just so perfectly symmetrical with multiplication, isn't it?
And once again, here's the formal equation that captures that rule. We divide the lengths and we subtract the angles. The elegance here is just fantastic. I mean, compare this to messing around with conjugates. It's night and day.
Okay, so we've learned this new trick. It's clean, it's elegant, sure. But why does it really matter? What's the big takeaway from all of this?
Well, the real power of this form is that it shows you what's actually happening when you multiply or divide. It reveals the true nature of these operations. Multiplication isn't just some abstract algebra. It's physically a rotation and a stretch in space. And division is a rotation and a shrink. We've totally replaced complicated algebra with simple arithmetic, and we've gained a much, much deeper intuition for what's going on.
So ultimately, what we've really done here is we've changed our perspective. And by doing that, we've turned these complex, error-prone calculations into a few simple, intuitive steps that you can actually picture in your head.
And that leaves us with a really fascinating question, right? If multiplying complex numbers is just adding their angles, what does that mean for raising a number to a power? Or what about finding its roots? Well, that simple insight unlocks a whole new level of mathematical power.